Good morning everybody. So, we are talking about the different sulfur compounds and how we can produce industrially those compounds which are also important in different reactions and other industrial processes. So, we are talking with sodium dithionite is Na2S2O4, which is the reduced version of your sulfur dioxide molecule. So, if we have sulfur dioxide, as we know that we can produce huge amount of sulfur dioxide by simple burning your elemental sulfur, what we get from the earth crust or from some sedimentary level or the sedimentary rock level. So, when we have sufficient amount of sulfur dioxide in our hand, the next thing is that what we are doing, we try to reduce it, and we have seen that your sodium amalgam was also useful, sodium formate was also useful for that particular reduction. And today we take another example where the typical reducing agent what we use in the laboratory, the sodium tetrahydroborate thing, that is NaBH4, that means the hydride ions will be used. That means it is a hydride reduction process where sulfur dioxide in strongly alkaline aqueous medium is treated with sufficient amount of that sodium borohydride. So, what you have in your hand therefore, that our plan is to reduce your sulfur dioxide and that sulfur dioxide in strong alkaline medium, because this particular one, the reactivity of this thing is dependent on the pH of the medium. Industrially also it is very useful to consider the corresponding pH medium or the range of the pH where the reaction is taking place, because this sodium borohydride is a hydride species, because you have large amount of H as H minus, and these H minus can very quickly react with your water molecules. Here we see we have not written anything on the left hand side as your water molecule, but we are producing 6 molecules of water on the right hand side. So, in alkaline aqueous medium, definitely we should also have water on the left hand side, but that water is not solely reacting with borohydride species, destroying it as for the production of hydrogen H2, because your borohydride can also be utilized for the production of hydrogen gas, and that hydrogen gas may or may not reduce your sulfur dioxide, but we should also be careful for this reaction condition. So, when NaBH4 is reacting with 8 molecules of NaOH and 8 molecules of sulfur dioxide, it is giving 4 molecules of Na2S2O4, that is our desired product. Where we are looking for the typical reduction of your sulfur dioxide giving you sulfur-sulfur bond for the formation of H2O4, and sodium borate is also forming, and 6 molecules of water. If it is not effective in reducing this particular one, sodium borohydride through some side reaction can be destroyed through its reaction with water molecules producing sodium borate. So, we should be careful about knowing all this composition of this reaction. And this dithionite, this Na2S2O4 has huge applications, and we should know, because we are all the time what we are looking for is the production, how industrially in a big scale we can produce this particular one, and what are the areas where this particular material can be useful. So, from application wise, it is important reducing agent in the dyeing and printing of textiles. So, where we all the time we require some reducing agent for coloring the textile material or the printing material. So, the reduced form, because sometimes we find that a dye you have and the dye is not colored in its original form, that means in the oxidized form, you can reduce it to its reduced form, and the reduced form is colored. So, fixing the dye to the printing material, the paper material or the textile material can be followed through the treatment of your sodium dithionite, which is a useful reducing agent. So, dye can also be reduced and giving you the coloration. And also sometimes it is used as a bleaching agent in the textile and paper industry. Sometimes we want to destroy some these dye molecules or some other material which can be reduced very easily by the treatment of your dithionite and can be washed away from this textile and paper material. So, is also useful as a bleaching agent. As we all know that the typical sulfur dioxide, the sulfur dioxide gas itself or sodium bisulfite NaHSO3, these are also very good bleaching agent in terms of their capability of reduction. Since they are very useful reducing agent, they can reduce this and it can show some kind of bleaching action through that particular reduction. So, production of this useful reducing agent in the industrial scale is also a very important area of study. If we consider that what we are doing for this particular production, and if we consider that in the previous case what we have seen that we can use some amount of formate. So, or the some methyl formate is the methyl ester of formic acid in methyl alcohol can be utilized for the reduction of SO2 to produce your Na2H2O4. So, what we have in the reactor basically, so how you feed the reactor is being fed from a solution which we consider as the first feed solution, which is nothing but a saturated methyl alcohol solution saturated by the sulfur dioxide gas. Then the second one is again a feeder solution dissolving NaOH and sodium formate in water and in heating condition. That means you heat the system, that means you have sulfur dioxide for A, the first feed, then the corresponding reducing agent as the B, that means sodium formate is basically, and also some solvent medium. The medium is in terms of your methyl alcohol and methyl formate. So, three of them we together mix up and the feeding together while stirring and heating the reactor. So, this is the reactor, and initially for the reaction we heat it, and then your methyl formate is reduction equivalent is being transferred for the reduction of your sulfur dioxide molecules, is also producing carbon dioxide. So, you have to remove that carbon dioxide. So, a path is there from the reactor which is nothing but your venting path for CO2, and when the reaction is over you cool the reactor contents. So, some cooling arrangement should also be there, or you can transfer it to some other chamber where the material can be cooled, and then it is passed for recovering through filtration. So, a saturated solution of your sodium dithianate can be in your hand, and that particular one can be evaporated in open basin or some other technique for crystallization. So, crystallization of that particular saturated solution will give you a good quality of your sodium dithianate or good crystals of your sodium dithianate, because it has a very good crystalline nature in the solid state. So, this particular procedure what people can adopt, and is mostly all these industrial processes are dependent on the company what they are producing, but is protected through some patent. So, it is the patent of Plantovich who has done or implemented this for a simple reduction by sodium formate. So, if we consider any other reducing agent, so you should have the mechanism, a different mechanism for treating this B to the mixture of this sulfur dioxide in some solvent or in some aqueous medium. So, next we go for some typical molecule. Sometimes if we consider that we are doing something, but we are not in that particular domain where we can consider about the bulk quantity of organic molecule, because in this particular class we are focusing only on some molecules which are of inorganic interest. So, inorganic chemistry. So, this is because the class is devoted to industrial inorganic chemistry, but some useful organic molecule can give you the very good example that how quickly we can make some useful molecule out of that particular knowledge, which is here as the example of sodium hydroxymethanesulfinate. Try to read the whole molecule as a name. Is not even your IUPAC recommended nomenclature, is a simple standard nomenclature, because it is a sodium salt, some hydroxy function is there which has been derivatized on the methane backbone. So, you have the methane backbone and then the sulfinate function at the end. So, it is a very simple molecule therefore. So, you have the sodium salt is basically a typical salt, you can consider as the organic salt, and at one end you have this hydroxymethane part, that means it is CH2OH, which can be derived from your methanol. So, methanol is CH3OH, but it is CH2OH. So, one of the hydrogen is replaced by your SO2 minus function. It is not SO3, remember that, it is not SO3, not even SO4, because we have seen that for making the detergent material, the SDS molecule, the sodium dodecyl sulphate we have introduced is as a sulphate. That means oxygen of the alcohol molecule is converted to a sulphate species through the attachment of SO3 group on O. But this is something different, where you can have a carbon sulfur bond, and not only carbon sulfur bond, but the functional group which is attached to that other part is SO2 minus, is not SO3 minus or SO4 minus, is SO2 minus. That is why the name is named as sulfinate, which we get basically from our previous molecules. What we are discussing so far is your dithionides, the Na2H2O4. So, dithionite is basically giving you this particular reaction in a very simple way, is a very simple technique. You should know only what are the reagents you will be using for the production of this particular molecule. We take formaldehyde only, CH2O, you know that is HCHO, is formaldehyde, single carbon aldehyde, is the simplest possible organic molecule in the aldehyde family, like your methanol or water molecule. We should all know is a one carbon bearing aldehyde. So, that basically the CH2O function. So, that CH2O function is being attacked by your dithionite in strong or medium alkaline medium of sodium hydroxide. So, you quickly look at the corresponding reaction, that is, you have the corresponding reaction from this particular one, as your sodium is not sulphate, is dithionite. Dithionite is formaldehyde plus water, is Na2H2O4, is not S, is Na2H2O4, is a mistake there, there is Na2H2O4 is reacting with HCHO, which is your formaldehyde, then water, giving two of these species. One is the corresponding sulphide function, that means SO3 minus, and another is SO2 minus. And this particular molecule, which is the sulfinate molecule, is the other one. So, basically what we are getting, that particular one, the reactivity of this H2O4 formaldehyde molecule is giving us one of the oxygen. So, you have some extra oxygen. So, it is not disproportionating between two SO2 fragment. One will be SO3 fragment and another will be the SO2 fragment. So, our desired material is the second one, which is having a corresponding carbon sulfur bond, and carbon to sulfur bond is attached to a function which is SO2 minus. So, this particular molecule is also a very useful one, because this sulfinate molecule is used in direct discharge printing for converting vat dyes. Because in the dyeing industry, people know the container, the reaction medium where they do the reaction is the vat, and in that vat the dyes are formed, and the vat dyes are utilized into their leucoform. Leucoform means their colorless form. So, you have to discharge the corresponding printing in such a way that either, as I told you, that the colored form is the reduced form, and sometimes the leucoform, that means the colorless form, is also the reduced form. So, again, in relation to your dye industry or the printing industry, you use not directly the Na2H2O4, but this methanesulfinate molecule for that particular purpose. It is also a reducing agent in redox initiator systems for emulsion polymerization. So, in a typical polymerization step, if we can go for a reducing agent, that means sometimes we know that during polymerization we can have a oxidation or we can have a reduction. That means electron transfer is taking place for a particular type of polymerization, and if you have the corresponding material as emulsion, so it is known as emulsion polymerization. So, as a reducing agent in a redox initiator, because sometimes we know that if it is a chain reaction type of thing, some reaction which is initiated. So, electron transfer reaction can be initiated by addition of this particular reducing agent. So, instead of your dithionite, you can have this methanesulfinate as a very good useful reducing agent for emulsion polymerization, and the molecule can also be broken very quickly for its components. Then we just take the example of the very old and very well known molecule is the hydrogen sulphide gas H2S. We know the stock of our hand, which is your sulfur, and from the sulfur how we get sulfuric acid and all other sulphide bearing or the sulfur bearing compound. This particular one is a typical reduction process. So, we are moving in the opposite direction. For making sulfuric acid, we have oxidized your sulfur to sulfur dioxide and then to trioxide. Now, what will you do? We just simply reduce the elemental sulfur or the pure sulfur what we have in our hand, and that particular sulfur in hydrogen. So, solid sulfur, yellow colored solid powder material as the sulfur with a gas discharge of hydrogen gas. So, hydrogen, you can have a huge source of hydrogen in the different areas. We all know that hydrogen can also be obtained from your natural gas sources or simply the methane source, if you not get the hydrogen from water or hydrogen from any other sources. So, that hydrogen, whether you are getting it through in situ generation or from the cylinders or from some any other source. So, that hydrogen at a temperature of 350 degrees centigrade in the presence of catalysts. So, you should require some catalyst for that particular conversion. That means the reaction of your hydrogen gas with elemental sulfur. What is that? It is nothing but cobalt molybdenum oxide. So, is a two metal oxide system, is not a cobalt oxide only or molybdenum oxide, but is a cobalt molybdenum oxide, and that cobalt molybdenum oxide on a surface of gamma alumina. So, gamma alumina surface is used, and on the surface you have the layering of that particular catalyst on which you can have a mixture of this sulfur and which is being passed through your hydrogen gas. So, this hydrogen sulphide what you can have in your hand can be very useful also, because we will see also how we can make other sulphide salts. The most important one is your sodium sulphide. How we get this sodium sulphide, because sodium sulphide also have some huge applications. But for this H2S, it can be a starting material for the manufacture of sodium hydrogen sulphide, NaHS. So, you have two hydrogen centers or two hydrogen atoms attached to the sulphide center, and if we can replace one of the hydrogen by sodium, you get NaHS or Na2S, which is sodium sulphide, or different types of organic sulfur compounds. Large number of organic sulfur compounds we can have, we can make also, such as thiophene and different thiols. Even the biological molecules we have, the sulfur bearing amino acids also we have. So, the sulfur assimilation in terms of the supply of inorganic sulfur what we are getting from the naturally available sulfur source, and that sulfur source can be utilized for incorporation of sulfur in thiophene say. So, production of thiophene is therefore dependent on the production of your sulfur and some other important molecule which are sulfur based for the right introduction of sulfur in your organic backbone. Where we get this? Because this, as I told you, that is from the raw natural gas or biogases, because both of them are the corresponding thing what is present there is the methane. So, CH4 is the main constituent of this, and it also has some amount of H2S, because the sulphide or sulfur bearing molecule, because the biomolecules also can have sulfur because it has the protein origin, amino acid origin. So, sulfur bearing amino acid, so any other sulfur source can be reduced to your hydrogen sulphide. So, when we take out your natural gas or for bottling your CNG, the compressed natural gas or any other biogas source, it can have the corresponding hydrogen sulphide in it, and how you remove it. So, you should have a technological knowledge for that. That amine is utilized for gas treating technologies, is first converted to its ammonium salt. So, if you have H2S, if you directly use ammonia or any other amine, you get ammonium hydrogen sulphide or ammonium sulphide, whereas the pure natural gas which is your methane is remain unaffected. So, the basic reaction what we will be looking for, either you have a organic amine molecule, and that organic amine molecule is nothing but your RNH2. It can be your ammonia also when R is equal to H, which is being treated with H2S, any contamination or any other source giving you the corresponding RNH3SH salt. When they are together in solution, they are separated away as cation, as the anion, but when you try to isolate it from the salt like sodium chloride isolation, you get the corresponding ammonium bisulfide salt. So, ammonium bisulfide salt you can recover it as some value added product through that. So, recovery of that thing in terms of its corresponding salt is also achievable for the entrapment of your hydrogen sulphide in the natural gas. So, next we will see how we can go for your corresponding salt. The typical whole salt is your sodium sulphide S. As we have seen that we are talking about H2S. So, you have Na2S. So, you have to make this particular one, but if we try to produce it in some other source, because we know that we can have SO2 which is getting oxidized to SO3, then we have H2SO4, then we can make its corresponding sodium sulphate salt. So, what you see here is that you can have this from your this, because this we got from the sulfur, the natural sulfur source what you have. So, sulfur is getting converted up to this. Now, if I say that how will you make this, because it will be a very cheap source in your hand, large amount of sodium sulphate you can make from sulfur, the elemental sulfur, the ore sulfur or the mineral sulfur what you have as a reserve. So, what you do that is sulphate is the anion present and you convert it to sulphide. So, we should go for reduction. How? Carbon is the simplest way, is the carbon, that means the charcoal reduction process. So, the charcoal reduction process for your Na2S4 with that of your twice of C is giving you Na2S plus. So, that is the most simplest way of making sodium sulphide to you. What we use? We use some pot furnaces, your reaction chamber for this particular procedure, where we use this and we get a melt, because this particular sodium sulphate is a salt. So, we have to make a paste and that particular melt is mashed with water. Giving water, you mashed it, then remove the water insoluble material which is not going into water. So, what we try to get? We try to get the soluble part, the water soluble part from here. So, we get that. So, you have this. So, you get this. So, this is escaped away. So, you have the sodium sulphate melt out of this. So, you removed and you go for evaporation. And through that evaporation, you get corresponding enrichment, a concentration from 60 to 90% of this can be enriched, but roughly speaking it is remain and 60 to 62% basically achieved, because the high range is not very easy to achieve. So, 60 to 62% is there. Then we go for crystallization or solidification. So, it is solidified at high temperature, say about 90 degree centigrade. That means, at 90 degree centigrade you get the corresponding saturated solution, and that saturated solution is allow for your crystallization. So, you will get good amount of your sodium sulphate crystals in your hand. So, this is one particular technique what we can have, that one basically we get there. That one particular process also is known as your electrolysis process. In that particular process, in electrolysis process, if we make some new species like Na2S4, what is this? We have seen that we can have a sodium sulphide, you can have sodium dithionite. Now, we are talking something which is Na2S4, that means it has a charge of 2 minus. So, S4 2 minus, so that means is a species of this type having a charge of 2 minus, which is nothing but a species which is known as polysulphide. So, this is your tetrasulphide. It is very easy to make also. In solution we get sometimes, instead of simple sulphide you can have the polysulphides also. So, this tetrasulphide which is S4 2 minus, and that we also produce from Na2S itself with some amount of elemental sulfur, giving you Na2S4. And if we go for that is reaction with sodium amalgam NaHgX, with that giving 4 Na2S plus 6 HgX, mercury free mercury. So, is basically this sodium is coming from your sodium sulphide salt for production of this sodium sulphide. So, this is the one way. So, this is also in this particular process, it is electrolytically produced. So, we produce this particular one. So, you see that we consume sodium sulphide, then we convert it to some polysulphide which is tetrasulphide over here, then again we react with sodium amalgam to get back your sodium sulphide and mercury. So, this particular one can also be utilized to purify the material if your sodium sulphide is a crude one. So, because this electrolytic technique or the electrolysis process is giving you high purity material. So, the high purity material can be obtained through this particular procedure, and then we see the different applications. So, the different application, first one is in leather industry. So, sulfur and sulphide, one thing we know that the removal of the hair of the animal skin. So, in the leather industry, the sulfur bearing compound for this particular reduction reactions is very useful. Then it can have for ore flotation, TION, ore flotation. So, for floating the ore basically. So, this particular solution, saturated solution of sodium sulphide can be useful, and your this particular solution is also useful. Then in textile industry, again for the different types of reduction reactions, you can use. So, those reduction reactions can be useful for your decolorization or the change in the color, or sometimes for achieving this particular color. And in the polymer industry also, in polymer industry. So, if you simply think that we can have your sodium tetrasulphide in your hand, a solution, or sodium sulphide in your, and how you can help a particular material in polymer industry, that will see for your thing that how this is there, that means you have to incorporate sulfur. So, it will be a sulfur based polymer you have to incorporate sulfur in it. That is why your sodium sulphide or sodium polysulphide can be useful in polymer industry. So, one very useful one this polymeric material is known as PPS, polyphenylene sulphide, which is nothing but polyphenylene sulphide. Because this is industrially useful, is a high temperature resistant material So, if you want to make a high temperature resistant polymer, we can go for some sulfur backbone in it, and that sulfur backbone can be introduced from sodium sulphide only. So, you have this, so you have therefore the phenyl ring backbone, the sulfur and this. So, these two positions basically is getting polymerized. So, you have this polyphenylene sulphide. So, you have this phenyl sulfur is a long backbone of these things. So, then coiling of all these things and all other things can be obtained from this. So, if we make some useful industrial polymer, then again we take the help of simple molecule like sodium sulphide. So, you should know what particular inorganic compound which can be produced in a huge quantity is be useful for making a polymer bearing sulfur, that means sulfur in it. So, after this sodium sulphide, the other one, that means if we can get the bisulphide, which is also useful, that how you make the sodium bisulphide species. Now, you have seen that how you can make hydrogen sulphide, and that hydrogen sulphide, because these two hydrogen you can replace from this particular sulfur. So, now one of them can be used, and you have in your hand, this is your basically HS minus the bisulphide ion, because these bisulphide ions are again very much useful for different purposes that we will see, and what are the reactions basically we will see in our next class, that whether we can use directly your H2S or whether we can use sodium sulphide. So, two things you can have, either you can incorporate or make it a monosodium salt, one of the sodium ion can be replaced, or you remove one of the sodium from here to get the corresponding one with the introduction of a proton. So, these two things we will see that you can have plenty of hydrogen sulphide in your hand and plenty of sodium sulphide in your hand. How these two things can be separately tackled to make your sodium hydrogen sulphide, that we will see in our next class. Okay. Thank you very much.